Hi everybody, I'm going to go ahead and get started. My name is Allison Alcott and I've been working at Rockware as a trainer and consultant since 2000. Thank you very much for attending this webinar. During the next 15 or 20 minutes, I'm going to talk about some advanced stratigraphy modeling tools in RockWorks15. This outline shows the sequence in which the information will be presented. Please feel free to type your questions into the GoToMeeting chat box at any time, and we'll either answer them during or after the presentation. The first thing I want to review is how a stratigraphy model is structured in RockWorks15. A stratigraphy model is composed of a series of stacked gridded surfaces as illustrated in the image at the top of this slide. When displaying the model in 3D, we add side panels to fill in the gaps between contacts and display it as shown in the image below. If a unit pinches out, it can be rendered transparent in areas where it doesn't exist. The grids that are used to construct this type of model are usually created through the Borehole Manager. They can also be created one at a time through the RockWorks utilities, or they can even be imported from another program like ArcGIS or Surfer. A RockWorks grid file is really just an ASCII file that contains header information defining the location and extents of the grid, along with a list of elevations in the grid. If you're going to put together a stratigraphy model yourself, you'll need to create a grid for the top and the base of each stratigraphic unit in the project. This slide gives an example of how the grids should be named. Each grid should have the exact same extents and cell spacing. If you've used another program to create some grids that don't match up exactly, you can resample them through the Grid Math menu and the RockWorks utilities. Next, I want to present a case study outlining the steps you would take to modify a model that was created through the Borehole Manager. I'll actually use our sample data set that is installed with the program to do this. In the figure displayed here, you can see that the model generally looks pretty good. However, if I strip away the upper units, you can see that this intermediate blue unit doesn't look quite right. Because the unit is relatively thick on the east side of the model and it pinches out completely on the west side of the model, the gridding algorithm used just isn't pinching the surfaces together as you would expect on the west side of the model. We'll be referring to this blue unit as the Leadville limestone in the following slides. The first step that I would take to solve this problem would be to create an isopack contour map of the Leadville limestone and plot labels showing unit thickness at borehole locations as well. I created the map displayed here by subtracting the base Leadville limestone grid from the top Leadville limestone grid through the RockWorks Utilities Grid Math menu. The labels were created through the Map menu in the Borehole Manager, and I was easily able to combine the two maps by copying and pasting the labels from one RockPlot 2D window into the other. I would next draw a polygon onto the map defining the extents of the unit. The polygon can be saved as a polygon table in the RockWorks project by right-clicking on it and choosing to save it as a polygon table. My drawn polygon is displayed here with a hatch pattern. The next step would be to use the grid polygon filter to assign thickness values of 0 to any grid cells that fall outside of this polygon. The resulting map would look like this. The last step would be to subtract this new thickness grid from the grid surface that represents the top of the Leadville limestone to create a new base grid for the unit. This is done through the Grid Math tool in the RockWorks utilities, and the slide shows the menu settings for this step. Model A is the top unit, titled Leadville Limestone Top, and Model B is the modified thickness grid. Model C, which is the grid being overwritten, is the base of the unit, titled Leadville Limestone Base. I would then repeat the step to replace the top of the unit below the Leadville limestone. In this case, we're creating a new grid for the top of the Potosi Formation. One tip is that you should always back up your grids in your project directory before you start overwriting them like this. Now that I've gone through this process, I can regenerate the stratigraphy model through the Stratigraphy menu in the Borehole Manager to create the model displayed here. You can see that the unit is now limited to areas just within the polygon that I drew to define the extents of the unit. Now I'd like to switch over to the RockWorks program and go through these steps just within the interface. So I'll go ahead and get RockWorks open. Everybody should see RockWorks on their screen. the first thing I'm going to do is I'll just go to the Stratigraphy menu and create a model. And by the way, I'm starting with a completely blank project at this point. You can see over here that I have no grid files, I have no solid models created. I haven't really done nothing in this program other than load the data. I'll go to the Stratigraphy menu and choose Model. And I have Interpolate Surfaces checked on right here. So what that's going to do is it's going to create a top and a base grid for each unit in the Stratigraphy types table. All right, so here's my 3D model displayed in RockPlot 3D. And over here in the data tree, I'm going to expand the stratigraphy model, and I'm going to check off the A horizon and the Spurgeon formation so that I can look at this blue unit, which is, again, the Leadville limestone. If I turn off the Leadville limestone, I can see that I would expect that the contact to probably go right along this line right here that I'm drawing with my mouse. So what I'm going to do next is I'm going to go through the process that I displayed in the slides to revise the extents of this model so that it more accurately represents my borehole data. I'll go ahead and close this window. The first thing I'm going to do is I'm going to create a map that includes labels that display the thickness of the unit. And I can do that through the map menu right here. I'll go to Map Borehole Locations. And under the borehole symbol and label options, I have stratigraphy data checked on right here. And I'm telling the program to plot Leadville limestone data, and I'm telling it to actually plot the thickness of the Leadville limestone. So I'll go ahead and click on the Process button, and this will just create a basic point map with labels that show these thicknesses. What I'm going to do next, I'm going to transfer this map into an undocked window so that I can use it later. So if I click on this button right here, I now have an undocked RockPlot 2D window that I'll just go ahead and minimize and save, and I'm going to close this window right here. The next thing I'm going to do is I'm going to go into the utilities. But before that, let me talk about the grids that have been created and are now displayed in the project manager. You can see that I have a top grid and a base grid for each stratigraphic unit. The program also generates grids that have clipped listed in the titles after them, and those are actually just created if you have the hide thin zones option displayed during the model creation. When you're starting to modify and edit grids like this, I would recommend that you work with these grids, not the clipped grids. The clipped grids will be regenerated once you regenerate your model using your modified surfaces. So it's these top and base grids that I'm going to work with in this case. So I'll go to the utilities, and I'll go to the grid menu, and I'll choose Math, Grid, and Grid Math. And I've set it up already here. I've got the Leadville limestone listed as Model A, the top, and Leadville limestone base listed as Model B. My operation is subtraction, and Model C is my Leadville limestone thickness grid. So I'm creating a new grid called Leadville limestone thickness. I'll click on the Process button. I'll go ahead and assign kind of a custom color interval, and I will get a map that looks like this. The next step is I'm going to go ahead and copy those labels onto this map. So I'll open up this map right here. I'll go to the Edit menu and say Select All, and I'll choose Control-C on the keyboard with my mouse to copy this information. And now I'll do Control-V to paste it into the window. So this is kind of a neat trick that a lot of people don't realize you can actually transfer really easily data from one RockPlot 2D window to another with the copy and paste tool. The next step will be to draw the polygon. So I'll go to the Draw menu and choose Line Types and Polygon. And I'll use my mouse and I'll use these labels and the contours as a guide to kind of estimate where I think this stratigraphic unit should pinch out. And I'll make the polygon go all the way around the project area. And I'll double click to finish the drawing of the polygon. So now that the polygon is displayed, I can select it with my mouse, right click, and choose to save to a polygon table. and I'll name this polygon table Leadville Limestone. All right, so now the next step is to use the polygon filter under the grid menu to render all of these grid cells over here, or to convert the values in those grid cells to values of 0. So I'll go ahead and close this and go back to the grid menu and choose Filters, Polygon Clip. My input grid is going to be that Leadville Limestone thickness grid that I just created. And I'll create a new grid called Leadville Limestone Thickness Polygon Clipped. And my polygon vertex table that I'm going to use is called the Leadville Limestone. That's the one that we just created. I'll tell the program to do an exterior filter type where the new exterior value is 0. And I'll go ahead and click on the process button. Now this is a display of the new contour map, and you can see that the thickness values in the contour map go from, right around 25 to a value of 0 based on that polygon that I used to clip the grid. Now I'm going to go back into the grid math menu, and I'm going to subtract this new isopack thickness grid from the top of the Leadville Limestone to create a new Leadville Limestone base. So I'll go to Grid, Math, Grid and Grid. Model A is still going to be my Leadville Limestone top grid, but Model B will now be this thickness grid that's been polygon clipped. And Model C is going to be the Leadville Limestone base. So I'm actually overriding the Leadville Limestone base grid in my project. I'll click on the process button, and here's a contour map of what that grid surface would look like. And then the last step is to overwrite the top of the Potosi Formation, which is the unit that falls below the Leadville Limestone. So I'll change Model C to the Potosi Formation top grid, and go ahead and overwrite it. And you can see that the contour map looks exactly the same because we're replacing the base of the Leadville Limestone with the top of the Potosi Formation. They should be one and the same. So now if I go back to the Borehole Manager and go to the Stratigraphy menu and choose Model, I'm going to regenerate this model, but I'm going to do one really important thing, which is turn off the Interpolate Surfaces option. This means that the program will look in my project directory at those grids that we just created or modified and use those to build the model. I'll click on Process. And here's my new model. And if I strip those two upper surfaces away, you can see that I have a new contact for this Leadville Limestone unit. One thing to mention is that it's a pretty steep contact. We have some tools, and we have a tool called the grid editor in the program that I might use if I wanted to make this contact less severe. The grid editor would actually allow me to smooth the grid, the thickness grid, only along this specific area using my mouse. So the grid editor is a nice tool for just making kind of manual tweaks of grids that you've created. All right, so I'm going to go ahead and get back into my presentation, and the next thing I want to present is a case study of a project that I worked on recently where we really had to manually build each stratigraphic surface separately. I want to thank Richard Brost with Four Corners Environmental for allowing me to present this data. The model displayed here is composed of 3 stratigraphic units and the BLUEWATER lake, which was treated as a stratigraphic unit in the model as well. We faced 2 main challenges during the creation of this model. The first was a lack of well-distributed borehole data. We had a very limited amount of borehole data just for a single stratigraphic unit. The second was the presence of a fault that was running along the eastern edge of the lake, and that's circled in this image. Luckily, we were able to treat this as a vertical fault, which was much simpler than trying to represent an angled fault plane. I should mention that the tools that you would use to create a model like this would really vary from project to project, and this is a fairly complicated model. This case study is meant to simply showcase some of the techniques that you might use to create a model if you had limited borehole information stored in the database. We constructed the model based on a few different types of information. We used a DEM that was downloaded using the Global Mapper software and converted to a RockWorks grid, an AutoCAD drawing of mapped geologic contacts that also displayed bedding orientation measured in the field. And notice that that bedding orientation kind of varies along each contact. It's not completely 100% constant. And we also had data for the top of the KBAB unit, which is taken from a publicly available database of groundwater wells. And those are displayed in this lower unit as the little blue cylinders. Those are actual contacts in the subsurface. The first step was to convert the geological contacts in the CAD map into data that could be used to create the stratigraphic grid surfaces. We did this by importing each DXF polyline into the RockWorks Utilities datasheet through the File Import DXF menu. This converted the vertices and the polylines to XY points. We then extracted the ground surface elevation at each XY point from the DEM through the Grid Statistics Residuals tool. This gave us a list of XYZ values along each contact that could be used in conjunction with the water well data to generate gridded surfaces. Unfortunately, the combination of the geological contact points and the borehole data just wasn't enough to create realistic grids. In this map that we're showing here, the blue points represent water well data where we had recorded elevations for the KBAB units. And again, that's the lower unit in the model. As you can see, these points are really limited to the area to the south of the lake. So the next step was to use the mapped bedding orientations to create some additional control points in the northeastern and southwestern portions of the area for each surface. So we projected some planar surfaces through the points along the contacts based on the measured bedding orientation in the area and pulled elevations from those planar surfaces. This projected data, which was, by the way, both below ground in the northern part of the area and above ground in the southwest, was combined with surface contacts and borehole information to create one list of XYZ values for each stratigraphic unit in the model. Now that we had the data put together, it was time to build the model. We did this one surface at a time, starting with the lower KBAB unit. The creation of this surface was the most challenging because it was intersected by the vertical fault that I mentioned earlier. We created one surface for each fault block based on separate lists of XYZ values and then merged them together into a single surface by using the grid polygon filter. In this image, you can see the merged grid and the polygon used to define the eastern fault block. Now, I mentioned previously that when we created additional control points using the measured bedding information, we chose to create control points both above and below the current ground surface. And we did this because we found that it is typically much easier to create a realistic subsurface grid if it is reconstructed above ground as well. This also makes it much easier to create surfaces that intersect mapped geological contacts. The next thing we had to do was get rid of the portion of the grid that was above the ground. So we used the grid limit filter, which is also available through the utilities, to truncate the surface in areas where it extended above the DEM. In areas where the surface was projected above ground, we replaced the grid cell values with elevations from the DEM. The final KBAB surface is displayed in this lower image. It's really a combination of 3 original gridded surfaces, and this was all done using tools that are available in the RockWorks utilities. Once the top of the KBAB, which is the lower blue unit in this image, was finalized, we used it to represent the base of the Zuni mountain formation that lies above it. We used a similar method to create a grid for the top of the Zuni mountain formation, which is displayed with the fuchsia color. And the top of the Zuni mountain formation was then used as the base of the Shinnerup, which is displayed in the dark purple. Because the top surface of the Shinnerup unit was weathered away, we were simply able to just use the DEM grid as the top of that unit. The diagram above was created through the Stratigraphy model menu in the Borehole Manager. And I want to mention again that when building a model using grids that you've created outside of the Borehole Manager, it's very important that the Interpolate Surface option is checked off. This is circled in the image above. This setting tells the program to look in the project directory for the appropriately named grids rather than interpolating them from the data stored in the Borehole database. Also, checking on the hide thin zones option will render the units transparent in areas where the elevation is the same for both the top and the base grids. The last step was the creation of the base surface for the BLUEWATER lake formation, and I did this by creating a grid composed of all zeros, and this can be done through the Grid Initialize tool in the utilities. And I then used the grid polygon filter to assign a value of 30 to all of the grid cells that fall within the lake polygon boundary. In this model, the lake has a constant depth of 30 feet. If we'd had detailed bathymetric information, we might have been able to vary the depth of the lake throughout the model, but we decided in this case to just keep things simple and give it a constant depth. I subtracted this lake thickness grid from the DEM to create a BLUEWATER lake base grid. And here's a view of the resulting model. I should mention that as a final step, I clipped all of the units based on a larger polygon, which gives the model this shape. This concludes this presentation, but before I pull up my final slide, I want to direct you to a few case studies on our website that will talk you through some of the processes mentioned in this talk, and also introduce you to some that we weren't able to cover. So what I'm looking at now is just our website, and if I go to the RockWorks page, and then to support and to case studies, what I want to take a look at is the case studies covering stratigraphy. Both of these, I think, give really good overviews of lots of different tools available in the Borehole Manager that can be used for either editing isopac grids or, truncating one surface against another. So if you have intersecting surfaces, the grid limit filter is a really great tool for that. So I would strongly suggest that you take a look at these case studies if you're getting started on a more complicated project and you kind of need an overview of the tools that are available. Also, please keep in mind that if you're getting started on a more complicated project, we're always happy to take a look at your data and make suggestions on how to approach the modeling process. I want to leave you with this slide that lists ways to get more information about the program. Our next in-house workshop, which is held in Golden, Colorado, is scheduled for April, and we still have a few seats available. Also, keep in mind that we're always available to schedule custom online training sessions. Thank you for joining, and we'll go ahead and see if there are any questions now. Okay, well, it doesn't look like we have any questions today, so we'll go ahead and end the meeting. Thanks again for attending. Have a good day.